Hello and welcome back. This is Dr. Kofel with Calhoun Community College, and I'm continuing my radioactive and nuclear chemistry discussion. And today we're going to talk about radioactive decay. And this is kind of a throwback to the kinetics chapter. When we did that, if you're in my class, we did not cover this particular type of calculation because I knew we were going to do it in the nuclear chapter. So if you're not in my class, you may have already had this. So just bear with us. There are small amounts of radioactive materials in your air, ground, water, the stars, cosmic, whatever, even in the food that we eat. And so this is what we call background radiation. So there is always a natural level of background radiation. And so when um, we do assays for this, we want to know what the exposure is to radiation or something like that. We always have to subtract out that background radiation because that's what you're exposed to all the time. And we know that that doesn't hurt us. Well, we hope it doesn't hurt us, right? So particles that are emitted by these radioactive nuclides have a lot of energy, and so we can detect that energy with several different ways. One way is we can use photographic film, okay, which kind of works like an X-ray a little bit. This can be used to detect the radioactive rays, and you'll see these a lot in hospitals and labs. This is called a film badge dosimeter. And this is the detector right here, and any type of high energy is picked up on this, and then it's held in there, and then they scan it, and it tells the person running the test how much you've been exposed to over what period of time. Okay, and so that's because there are levels that you are allowed to be exposed to, like within an 8-hour shift and things like that. Because these radioactive rays cause the air to become ionized, an electroscope can detect the radiation. And so what it does is it penetrates a flask and then ionizes the air that's found inside. And a Geiger-Muller counter or Geiger counter works by counting how many electrons are generated when argon gas is ionized by those radioactive waves. So you have argon gas inside this tube. This is our detector tube. All right, and we have a cathode end and an anode end. And these argon atoms, they go from argon to argon ion, okay, when they are, no, I guess they're probably negative. Don't really think about them being ions, but they ionize, so whatever the ionized form is. And when it's ionized, then that's picked up on a little amplifier, okay? And so then that feeds a signal to the amplifier, which then gives it a count, okay? So these charged argons then go to this detector. It counts them. It sends that count to the amplifier counter, okay? And then you have a voltage source in order to make this occur. So this is, you see these, this is like the industrial kind and the big, like this you see in movies and everything. You can get smaller ones, like we have one in the lab that we use that's made by Vernier. That's pretty accurate, but it won't get down low like this one, as low as this one probably. But the Geiger-Muller counter is an electroscope that detects the radiation by ionizing argon atoms. So this rate of decay is a first order kinetics decay, okay? So a degradation. The rate of change in the amount of radioactivity is constant, and it's also different for every single isotope. So you can see a graph for each one of those, and a constant that we look at is something called the half-life. And the half-life is the amount of time it takes for each radionuclide to lose half its radioactivity. Okay, so each half-life, it's lost half of its radioactivity. The shorter the half-life, the more decay per second. So it's a hotter sample. So if it has a short half-life, that means it's very radioactive. Okay? The rate of radioactive change is not affected by temperature. You know, kinetics a lot of times is affected by temperature. So because we know that it's not affected by temperature, we know it is not a chemical reaction. Okay, so it's not a chemical reaction. It's a process. Okay. So as I said, radioactive decay follows first order kinetics. And if you recall that from the chapter on kinetics and rates, that means that the rate equals some constant K times N, which is the number of radioactive nuclei. And so when we integrate that law, we come up with the natural log of the time, the number of the time you're looking at, divided by the initial number of radioactive nuclei, and that's going to be equal to a negative K, which is going to be a constant, times T, and T is the time. Okay, the half-life time, or the time. Okay, so how long did it take? And so if we rewrite this, we can convert that natural log to a log, and we can say that the half-life is equal to 0.693 divided by K. All right, so if we know K, then we can just use this particular formula, so it makes it kind of easy. If we don't know K, then we have to apply that natural log formula. And so this is just an example of some of the half-lives of some common nuclides. Thorium, for example, you know, a billion years, okay? U-238, almost that long. Carbon-14, 5715 years. Radon, 55.6 seconds. And thorium-219, nanosecond almost, right? Microsecond is what that is. So, I mean, that's super fast. So it runs the gamut, and it just depends, and each one is different, and it depends on how it's rearranging that nucleus when it emits that alpha particle. All right, so how do we figure these out? Okay, so when remember this is a rate. And so the first step we have to do is we have to find out what is the rate constant. And so the rate constant is lowercase k. And so to find the rate constant, you'd use this, or if you were finding the half-life, you could do this if you already know K. So in this problem, it's plutonium-236. It's an alpha emitter. It has a half-life of 2.86 years. So T1/2 is 2.86 years. If the sample initially, so that's N0, contains 1.35 milligrams of plutonium-236, what mass, so I'm looking for NT, is present after 5 years? So time equals 5 years. All right, so I want to know how much is going to be left after 5 years. All right, in this case, I know the half-life, and I know the initial concentration, and I know how long we're taking. So the first step I do is I'm going to plug that into this first formula, 0.693 divided by K, because I need to know what K is. Because I need K for the formula to find out actually what this N sub T is, right? So I rearranged this to K equals 0.693 divided by T to the 1/2. Okay, and I just rearranged that formula. If you want to plug the numbers in and then do it at the end, that's fine. I find this to be a little bit easier. All right, and so K is going to be equal to 0.693 divided by the half-life, and it told us that it was 2.86 years. 2.86 years. And so my units are going to look a little funny because it's going to be 0.2423 per year. Okay? All right, so that's K. So once I have K, I'm going to plug that into my natural log formula. So the natural log of NT over N0 equals a negative KT. Now, if I have a natural log, okay, and I want to get rid of natural log, I have to raise everything. I have to put e raised to the negative power, okay? E raised to the negative x, all right? So what I'm going to do is I'm going to do that. So if I raise this like that, see what I'm doing? And raise this to the negative whatever, okay, KT. All right, then what that does is I'm only doing that to get rid of this ln on this side. So then that gives me NT over N0 equals E raised to the negative KT so NT would equal N0, I got to multiply across, raised times E raised to the negative KT. So NT would equal N0, which that was the initial concentration of 1.35 milligrams, times E raised to the negative 0.2423 per year times 5 years. Okay, so that's my K, and my T is E is raised to that power. All right, and so when you put this in your calculator, make sure that you do your E and raise it to that, and make sure you get your parentheses right. Okay, and that's gonna, you should end up with 0.402 milligrams after 5 years. So you started with 1.35, and after 5 years you're going to degrade to 0.402 milligrams. So all this is really just reading your problem and then plugging it in to the example. And this is I did this one because this one's the hardest way, because you have to deal with the natural log and get rid of it. If you have like your practice problem, it's still referencing the numbers that we got in the first problem, so you know the half-life and stuff like that. But for this problem, you've got the natural log of two things you already know, so two concentrations. So you can just go ahead and take the natural log of that and make that a number, so you don't have to get into it. So this way I did it is the one that's the most challenging, because you have to get rid of that natural log when you have an unknown as part of that. Okay? All right, and that does it for part 3.